people. We're doing well today. Yesterday we started related rates, and I wanted to make sure that the multiplicity of different ways that related rate problems can be asked wasn't a distraction from actually understanding the logic of the related rates themselves. So I limited yesterday's discussion just to ones that were modeled, that could be modeled using Pythagorean Theorem. And that way it was always the same formula that we were using, and we could actually concentrate on, reading the questions and mining them for the information that we need and whatnot. Today we're going to extend that into the rest of two-dimensional geometry. Tomorrow we're going to extend it into three-dimensional geometry, and the day after we will entertain trigonometric related rates. And from there, of course, there's more than 4 varieties. Just basically use these first 4 days to sort of introduce in phases. After that, we'll have a firm grasp of related rates in general, and we can move on to basically entertaining any related rate that we are given. So, without further ado, let's go ahead and jump on in. If we're dealing with two-dimensional geometry, we're dealing with rectangles and circles and triangles. We're dealing with their areas and stuff like that, trapezoids and whatnot. This one is a rectangle problem, so we'll go ahead and read it. The length of a rectangle is increasing at a rate of 8 centimeters per second, and its width is increasing at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area of the rectangle increasing? Okay. Well, remember that we need to identify 3 things. Well, first of all, it's a rectangle. So let's go ahead and let's draw ourselves a rectangle, just especially for those of you who are visual. It's going to be helpful to actually, see things. So we have a rectangle. And we could do it with like length and width, but since we're used to using x and y, let's just go ahead and do that. So x and y. Now, the given information includes the length of the rectangle, which in this case we've designated as x. The length of the rectangle is increasing. So that is the rate at which x is changing with respect to t. It is increasing, so it is positive 8 centimeters per second. Now, it also gives us the rate at which the width is increasing. It's increasing slower, but it's at 3 centimeters per second, but it is increasing, so it's still positive. We need to identify the question. Now, this is an odd one because it actually asks the question last and gives us the conditional information first. And we notice that largely because we're able to, pick out the temporal word when. When the length is 20 centimeters, so when x is 20 centimeters, and when the width is 10 centimeters, so when y is 10 centimeters, how fast is the area? Okay, so we want dA dt. How fast is the area of the rectangle increasing? Well, just like the Pythagorean theorem, I simply need to come up with the correct formula before I differentiate. Obviously, I'm dealing with area of a rectangle, so it should be pretty, shouldn't be difficult to discern that I'm using A is equal to x times y. Now, just like the Pythagorean theorem puts the length of the legs and the hypotenuse into a necessary relationship, this formula puts the area and the length and width of a rectangle into a necessary relationship. Now, this formula will relate the magnitude of the area, the length, and the width. If I differentiate it, I will be able to relate not the magnitudes, but the rates at which those magnitudes change. So let's go ahead and differentiate. We're going to differentiate with respect to t, always, 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 because we're dealing with per second, right? So how fast does the area change with respect to t? And here I have to do the product rule. So it's the first times the derivative of the second plus the second times the derivative of the first. And it really is that simple. Okay? The two-dimensional geometry ones and the Pythagorean theorem ones don't require a whole lot from us. Some of them are a little, get a little bit intricate. It's the three-dimensional and the trigonometric ones that that will really kind of make us scratch our heads and kind of but we'll get to those. We need to, have the training wheel days before we get to riding the bike without them. So we're going to go ahead and just plug in, right? We have now the actual area formula was 3 variables, right? This is a formula of 5 unknowns. Well, I have 1, 2, 3, 4 of them, so I should be able to find the 5th. Now, dA dt. Now, x at the moment that I'm interested is 20 centimeters. My dy dt is 3 centimeters per second. My y is 10 centimeters. And my dx dt is 8 centimeters per second. Now that winds up being 60 and 80, so that's 140, and of course the units are now in terms of centimeters squared per second because it is area per time. Now that you have this, you would go ahead and write me a sentence, right? The area is increasing at 140 centimeters squared per second at the moment specified, or something like that, okay? Because is the area always increasing at 140 centimeters squared per second? The answer is no, okay? Now this next one, I probably shouldn't do this one second, but let's go ahead and just jump right in. Okay. A particle moves along the curve, and this is the curve. I've gone ahead and given you the graph. Y is equal to 2 sine pi x over 2. So that's basically pi over 2x. Pi over 2 is our b value, right? As the particle passes through the point 1/3, 1, so that's approximately right here, right? Its x-coordinate increases at a rate of root 10 centimeters per second. How fast is the distance from the particle to the origin changing at this instant? Now, it says as the particle passes through the point 1/3, 1, its x-coordinate increases. So actually, that is dx dt. But it's more conditional because it happens at the moment instead of ahead of time, instead of being consistent throughout the scenario. But it doesn't really matter because when I plug in, I'm plugging in for that moment in time, for that instant. And so whether it's given or whether it's conditional information really doesn't matter to me. So in terms of given, we actually don't have anything that's really relevant. I know that the question that I'm asking is how fast is the distance from the origin changes. So basically a particle is basically traveling along the curve, and of course if you can imagine it, like if the particle's over here, we would basically judge its distance, and so this is kind of Pythagorean. We would judge its distance based upon sort of the distance formula, and then we would differentiate the distance formula. But the distance formula, remember, is just Pythagorean theorem in disguise. So let's go ahead and designate just any old triangle which judges the distance. Let's call the hypotenuse z. This is of course x and y. So what I'm really looking for is dz dt. Okay, and I'm looking for it on the condition, on the condition that x is 1/3, right? I'm just reading that right off the ordered pair. Y is 1, and of course if that's the case, I can use Pythagorean theorem to figure out that that's root 10 over 3, right? And of course remember that the pieces of the conditional that are not specifically stated, I usually refer to as the implied conditional. Okay, well here's the thing. I could, remember that the distance formula is the square root of, x2 minus x1 squared plus y2 minus y1 squared, right? But remember that that's because it actually comes from the Pythagorean theorem. Okay. Now, in our case, however, we're using z instead of d. Okay. And the reason is I want to differentiate from something more akin to this than this, because I'm still going to get my dz dt, but I don't have, if I do it from here instead of from here, I don't have to worry about the radical. And I still wind up getting the same thing, right? So z squared, and in our case, this ordered pair right here, this 1/3 1, is our x1, y1. But we're looking for its distance to the origin. Actually, let's call this x2, y2, so we don't have to reverse. Our origin is the second ordered pair, right? But the thing is that this is the instant at which it happens. I'm actually interested more in the general form of this right here. So we're not going to use this for x2, y2. For x2, y2, we're going to use the fact that anytime you have a y equals, this can double as the y coordinate. So y equals 2 sine pi over 2x basically is another way of saying x 2 sine pi over 2x. All of the ordered pairs of this form. Okay, well that's kind of neat. And especially since x1 and y1 are both going to be 0, really you're just taking 2 sine of pi over 2x and you're squaring it. And then you're taking the x-coordinate and you're squaring it. Sorry, I did that backwards. This is the y-coordinate, this is the x-coordinate. But, you know, addition is commutative. So this represents basically the Pythagorean theorem for any ordered pair x 2 sine pi over 2x. Okay? So now we need to differentiate with respect to t. So we get 2z times dz dt is equal to 2 times 2 sine pi over 2x. And then, of course, we need to take the derivative of the inside. And the derivative of the inside is 2 cosine, sorry about that, pi over 2x times pi over 2. And then we need a dx dt. Thankfully, the next term is going to be much easier, 2x dx dt. Now let's clean this up. Okay, first of all, each term has a 2, so we can go ahead and cancel that out. So we have z times dz dt, and I have 2, 4, but that's pi over 2, so really together that winds up being 2 pi sine pi over 2x cosine of pi over 2x times dx dt. But if I just go ahead and put plus x, then I can factor out the dx dt, and I only have to plug it in once. Now, remember, I'm looking for dz dt. So let me go ahead and start way over here. The notation is sticky, but it's burdensome, but there's nothing in here that you don't know how to do, right? And you could take the 2, the sine, and the cosine and use the double angle. And I'm actually going to go ahead and do that. You don't have to, though. And so basically, if I take the 2, the sine, and the cosine, I'm going to turn it into pi times sine of pi x plus x, all of that over z times dx dt. And then I just plug in, right? Because now that I've differentiated, I can go ahead and plug in all my conditional information. Basically, when I plug in x, x is 1/3. That makes sine of pi x sine of pi over 3. Well, sine of pi over 3 is root 3 over 2. and then plus x, so that's plus 1/3. And then if I'm dividing by root 10 over 3, I know that it's going to be root 10 over 3, and then times dx dt. Well, dx dt, remember, I guess I should have included it here in the conditional because I didn't include it in the given. Dx dt at that moment is root 10 centimeters per second. So basically that root 10, okay, now remember that this is distance, and so it's basically the centimeters per second that's going to reign in terms of the units. Now, this root 10 cancels with this root 10, and basically to divide by that 3 is the same thing as, dividing by that 1/3 is the same thing as multiplying by 3. So we basically are 3 times pi times root 3 over 2 plus 1/3 centimeters squared. And you can go ahead and clean this up in a whole host of different ways. But we can go ahead and get a decimal approximation as well. So let's go ahead and do that. Let's go ahead and do 3 times, and we'll go ahead and put pi root 3, root 3 over 2 plus 1/3, and that winds up being 9.162 centimeters per second. And then you would just write me a nice little sentence explaining that. Now, that one was kind of difficult, and I probably should have saved that one for later. There is an easier one a little bit later in the problems that I've chosen for these videos. But ultimately, and this wound up being a Pythagorean Theorem one, and you know that won't. Sometimes that'll be evident right on the face of it, and sometimes Pythagorean Theorem will sort of be cloaked in what looks like a topic of something else, right? In terms of either, you know, a rectangle or a square or whatever, something where the right triangle can be inscribed within it. Let's go ahead, and this one is actually, okay, a nice little break from this one. This one is wonderfully simple, okay? But it's one of those, it's another one of those like the ladder problem that we discussed yesterday. It's one of those ones that is incredibly common, and it's one of those staple problems that everybody sees this one when they do related rates. Okay, so there is a, let's go ahead and, it says a 5-foot tall person walks away from a 20-foot tall street lamp. So let's go ahead and draw that scenario, and you have the person walking away and you have the street lamp. Okay, yes, not an artist. I've never claimed to be, guys. So what happens is, if you're looking at the shadows, shadow would do that, right? The tip of the person's shadow would wind up being right over here, right? Because it has everything to do with basically the light coming right over the top of his or her head. Now remember that the street lamp is 20 feet tall. The person is 5 feet. And of course, as the person is walking away, right? Person's walking away, the distance between that person and the street lamp gets larger. But also, you know, if a person's out here, the shadow's also going to lengthen, okay? Now, they want to know, right? Actually, let's go ahead, just one thing real quick. Given is the fact that the person is walking away at 3 feet per second. Okay, so the distance between the person and the lamppost is lengthening at 3 feet per second. Well, let's go ahead and name it. Let's call it x, so that we can actually name what's given. dx dt is 3 feet per second. That person is walking away. Now, it also wants to know, okay, so at what rate is the length of the person's shadow increasing? Okay, well, that is this length. So let's call that y. I know, we're being really imaginative. And so my question in part A is, at what rate is the length of the person's shadow increasing? So how fast is dy dt getting larger, right? And B, at what rate is the tip of the shadow, so this point right here, at what rate is the tip of the shadow moving away from the base of the street lamp? Well, that's going to combine both this distance increasing and this distance increasing. Now you can go ahead and call this whole distance like another variable, right? And call that, z, and call it, dz dt is equal to what? But z is just simply x plus y, and therefore dz dt is simply dx dt plus dy dt. So basically, once I've found the answer to part A, I simply need to add it to the given in order to get the answer in part B. Okay? Now, the conditions, okay, they don't give us any. Okay, well, if they don't give you any conditional information, then the only conclusion that you can come to, or there's two conclusions you can come to. There is information that is implied by the scenario that you are failing to recognize. So let's say that you're given a problem that has a clock, and it has to do with the motion of the clock hands. Well, if you're given a clock, you're given certain information that is implied, right? If it says, at 3 o'clock, well, that means that the, hour hand is out towards the 3 and the minute hand is up at the 12. But there's also sort of given rates and stuff like that. So, I mean, that's probably a bad example for what I'm trying to get at. But like I said, there are certain scenarios where they don't say anything, but the scenario in and of itself gives you information. Now, that's the first possibility. The second possibility is simply that the conditional information doesn't matter. Okay, well, here's the thing. I have dx dt, I need to find dy dt, and I need to figure out how to set up a relationship between x and y. Well, that's similar right triangles, guys. And similar right triangles, of course, have proportional sides. And that means that if, y is to 5, meaning this leg is to that leg, as x plus y is to 20. And, if I go ahead and cross multiply, and I'm going to get 5x plus 5y, and I'm going to get 15y is equal to 5x, or 3y is equal to x, what happens here is I recognize that if I differentiate this, if y is always 1/3 of x, or if x is always 3 times y, if it always is 3 times y, then if x is increasing, it must be increasing at 3 times the rate, right? In order to maintain that ratio, in order to maintain the ratio of 3 to 1, it has to increase at a rate of 3 to 1, which should make sense to us, right? And therefore, we know that dy dt then is equal to 1/3 times dx dt. Well, they gave us a nice, neat value for that. It's 3 feet per second. And dy dt winds up being 1 foot per second. And then, of course, if I come back over here to do part B, my dz dt is dx dt, 3 feet per second, and dy dt, 1 foot per second. And that gives me 4 feet per second for my dz dt. And so, we had triangles, but we weren't finding the area. We weren't using Pythagorean theorem. We're actually using the proportional sides idea from similar right triangles, which, gotta admit, kind of neat. Still triangles, but related in a different way and used in a different way for the purposes of our problem. Now that's a couple of examples. I'm going to go ahead and close this video, and we'll do, I don't know, it looks like I have enough for probably 2 more videos. Of course, it always depends on what kind of rabbit trails I chase down and what things I think of in the moment. But if you have any questions, as always, please do shoot me an email. Bye.